Let's minimize here. All right, and we said sampling is the process to go from continuous domain into discrete domain. So usually we have continuous signals, analog signals. I think it was discussed early in this lecture. Yeah, something like this. So you have a signal like this, you take at certain intervals or certain samples. And let's say if I want to take at like sample every 1 second, let's assume the time here is in seconds. So we'll say my first sample at 1 second. At 2, I have this value. At 3, I have this value. So I take the function output at each point in time. That is part of the samples I'm taking. So assuming that I'm doing 1 sample per second, or my sampling period TS equal 1 second. So this one, if I want to plot it, will be something like this, assuming that I'm starting from -3. So that's a 0, -2, that's a 0. At -1, I have a -1. So I'll do it. Okay, so it's a pulse like this. At 0, I have a 0. At 1, I have 1. And then I have zeros elsewhere. So this is what we call a discrete signal, and here we have x of t. In discrete, we call it x of n. All right, so let's talk in detail about sampling. So we briefly saw it. Slideshow from current slide. All right, so if we want to, let's say, convert between continuous and discrete time, so that's very often request. Usually signals in real life, they are all in analog or continuous. And we want to convert them into digital basically because computers understand digital, understands discrete values. So we have what we call a continuous to discrete converter, or in some cases we call it analog to digital converter. So that's the same thing. Analog is continuous, discrete is digital. So this is a process, what we call sampling. So you have an ideal continuous time to discrete time converter, something like this. Just a block, let's not worry about what's going on inside. So it does transform a continuous signal into what we call a sequence. We agreed that in discrete time, we don't call them function, we call them sequence. Now, if you want to do, let's say, going backwards, if I want to go from discrete into continuous, we have another device called discrete time to continuous time, D to C converter. And basically, since we have discrete values like this, so the method to fill the gaps between, let's say, those points, because in discrete time, if you're, let's say, there will be no values at these points. So to fill these gaps, to make them continuous, we use a method called interpolation. And there are plenty of algorithms for interpolation, bipolar interpolation, bicubic, etc. Just to show, let's say, going backwards from digital into analog. One important thing here, let's say we have, and by the way, this should be like this. And so let's assume if I have a continuous to digital, then the output, I'll put it back into digital to continuous. So I started from analog, converted to the digital, now the digital back into analog. Notice here they use the x hat of t, not exactly x of t, just because x hat of t is an approximation of x of t. They are not exact. And that's why sampling called an irreversible process. You cannot, let's say, get the exact same input analog, like in here, x of t. You cannot have that same x of t. However, like there are different optimization techniques to minimize the difference between x of t and x hat of t, like mean square error, similarity index, many other, let's say, algorithms to deal with that. So just keep in mind that sampling is irreversible or not invertible. Interpolation is the opposite of sampling. Sampling, I have continuous, I want to take samples in time. Interpolation, I have discrete time, I want to fill the gaps between those values. So this is the interpolation. So this is just the terminology of interpolation and sampling. All right, so mathematically, how do we do sampling? Basically, at discrete points in time, separated by a certain distance. And usually our sampling is periodic or with, let's say, equal distance. Means that if I take the sampling at Ts equal 1, that means every second I'll take a sample. All right, so although sampling can be performed in many different ways, but periodic or uniform sampling is a quite used one for simplicity. So with this scheme, so take say a sequence Y of samples obtained from continuous time signals according. All right, so again, now notice here, Y of n, Y is discrete. Now X is continuous, so I keep it like this. It means that I'm taking from the continuous time from the continuous signal at fixed point in times. Now for all integer values of n goes, let's say, from negative infinity to infinity. But the restriction, it is integer. All right, and t is a positive real constant. That's what we call, usually we call it TS, and stands for sampling period. Another term we usually use is the sampling frequency. Which is Fs, and mathematically it's 1 over Ts. The frequency is the reciprocal of time. All right, so this is if we use Fs, and here the unit will be in hertz. In many references, they use omega s, that equals 2 pi Fs, which is the same as 2 pi over Ts. And in this case, omega, the unit will be radian per second. Again, that's just some terminology. Most of our work will be dealing with Fs only. However, whatever is done applicable in Fs will be the same dealing with omega s. All right, so Ts is a sampling period, and omega s is the angular sampling frequency. That's why they call them angular, and the unit will be in radian per second. So this one is just the standard sampling frequency. So an example of a periodic sampling is shown below, where the original continuous time signal X has been sampled with a sampling period 10. So let's see that example below. So it says that every 10 seconds, I'm going to take a sample. Keep in mind this expression, X of n equal X of n Ts. Now my Ts is fixed. It is 10. So X of n equals X of 10n. I just substituted then 10 instead of Ts. Last semester I had, like in the quiz, I gave an example similar to this, and I was surprised. Many students, like, they don't know how to deal with this expression. So I'm taking samples. So my function starts from 0 until, let's say, 80. So to get a sequence X of n will be just a set of discrete values. So that's the first value, separated second value, third value, fourth value, and so on. Now, usually this is index number 0. The first position is index number 0. Second position, index number 1, 2, and so on. So we start from the 0 index. Now, at n equals 0, what will I have? I will have X of 0 equals, now substitute in this expression, X of 10 times 0, which is X of 0. Now this value here, I will get it from the continuous function. Remember, I have parentheses, that's the continuous function. I'll go to my continuous function. Here's my 0. So it's almost 2.5. So x of 0, 2.5. Now, at n equals 1. So I'll get x of 1. Remember, n are integer values. X of 1 equals x of 10 times 1, which is the value of n. So it is x of 10. Let's go to the function. X of 10 is approximately 3.5. So that's 3.5. And so on. X of 2, it will equal x of 20 from the continuous. My second sample at the 22nd. So x of 20 here, go there. So it's almost 2. X of 3, all right, so it's going to be x of 30. It's almost 1.5. Approximately, I'm giving approximations. X of 4, which is x of 40. And that equals approximately 2. All right, so I got my sequence points. How to plot them? Now my axis now is no longer time. It's index, it's n. So I'll just draw it like this. That's my x-axis. And here's the value x of n. Now, one important thing, now my values of n are integer values, 0, 1, 2, 3, 4. So I will start from 0, 1, 2, 3, 4. Now, x of 0, we found out that's 2.5, something like somewhere like here. X of 1, which is x of 10, it was almost 3 something. X of 2 is 2. X of 3 is a little bit less. X of 4, similar to x of 2, something like this, and so on. So when you plot, make sure you have them like this. You've done MATLAB before? You've done MATLAB, right? Okay, so when you want to draw a function in MATLAB, what is the command? Like this one, I gave you the expression and I ask you in MATLAB, draw that command. What is the command? Plot. And I will have the time axis and the x-axis, right? That's how we use it in MATLAB. Now, if I want to do discrete signals, how to do that in MATLAB? I will not use the command plot. I will use another command called stem. Stem command. I think you've done that in the course. Probably like one of the labs, you will deal with that with the engineer, I thought. But yeah, in MATLAB, if you want to plot a discrete signal, you use the command, you will use the command stem. But if you want to plot something in continuous, you use the command plot. Now, what will happen if for some reason, if I want to plot this function in MATLAB and I use the command plot? Basically, MATLAB will draw the function in continuous time and will fill the gaps by a straight line. It will do an interpolation. So this is how we do it in MATLAB if you use the command plot. But if you use the command stem, you will have the discrete signals. All right. All right, so that's about, I believe, sampling. So sampling process is not generally invertible. We've seen that from these two slides. However, there are some conditions that if we apply, we can get, very close approximation to the original signal. And also, like sometimes sampling might not, if you sample at not proper values in time, you may get a 0. For example, if x of t here is very easy, x of t is 0, so it is fine. Like always, the results are 0. But let's say you have a sinusoidal signal, sine 2 pi t. Okay, and you said, you know what? I want to sample every 1 second. Okay, so the first sample at x of 0, what you will get? Sine is 0. How much? 0. X of 1 equals sine 2 pi 1. Sine 2 pi, how much? 2 pi in degrees, how much? 360, full circle. So you went back to angle 0. So that's a 0. X of 2 sine 2 pi times 2, which is sine 4 pi. Again, that's another 0. Sine x of 3 sine 6 pi, that's a 0. So all your samples are 0, even though it's a sinusoidal, and we know sinusoidals have this shape. However, when you say that, okay, I want to sample at 1 second, so you're basically taking these angles. You have the first sample, second sample, third sample, and so on, fourth sample, etc. So you're always taking these 0 spots. All right, so that says that if you want to do sampling, there should be some constraints. A continuous time signal cannot usually be uniquely determined from a sequence of equal spaced samples. Also, consider, for example, this continuous signals. So x1 of t, if you do the sampling, and x of t sine pi of t, if you consider sampling period equals 1, both of them will give you 0 samples. All right. So in this case, you cannot distinguish like this 0. Is it coming from x1 or x2? For all non-integer values t, fortunately, under certain circumstances, and that's what we'll talk about. Have you heard of the word Nyquist before? Nyquist. All right, so this is going to be our condition. Like we have to sample at least larger than the Nyquist rate. Okay, so how do we perform sampling? Usually sampling is performed by what we call an impulse train. We'll talk about the impulse in a few minutes. So basically you have your signal, you multiply it with an impulse train. An impulse train is basically just a train of impulses. So when you multiply any function with this train of impulses, and these pulses are of value 1, you basically remove the values in the function that does not fall into, let's say, these indices of the impulses. And this is what we call a delta function. More about it in the second lecture. All right. So the sample of continuous time signal to produce a sequence, multiply the signal by sample to be sampled by a periodic impulse train, and convert the impulse train to a sequence by forming a sequence from the weights of successive impulses. Just, you don't have to worry about this process. In the exam, you just follow this mathematical expression, and I hope this explanation, and we'll, like at the end of the lecture, there is an example actually, similar to the quiz of last semester. So we'll try and solve it in class. All right. Again, that's a graphical representation of sampling. So you have the signal continuous domain, and you have the train of pulses here. So this is where you get your samples, and that's your output sequence. Okay, so sampling theorem. So let x of t be a signal with a certain Fourier transform x. Suppose you've done Fourier transform in Math 2, transform or just series? Okay, perfect. So this should make things easier. So you have a signal with a certain Fourier transform, and suppose that the amplitude of Fourier transform is 0 for all omega satisfying omega over, let's say, larger than omega m. Basically, it's saying that your signal is band limited. Have you done this like in Fourier domain? Like that's the frequency response of a signal that is band limited. Like I have a maximum frequency and minimum frequency. So this is what the statement means. So it means that suppose that x of omega, the amplitude for all omega, let's call it f, x of f. And you have f, like omega equal to pi f. All right, so it says that the amplitude of the Fourier transform of this signal is 0 if the frequency is larger than a certain frequency, which is omega m here, or fm. Okay, so the signal is band limited and it's bounded between negative fm and fm. Then x is uniquely determined by samples, y of n. Again, that's a sequence, so it should be discrete. X n of t for all integer. It just says that you sample at least twice larger than twice the highest frequency of your signal. So let's say my signal frequency is 50 hertz. I need to sample at least at 100 hertz. This is the condition here. Again, same thing here, FM or the maximum frequency of the information signal. Okay, so if this condition is satisfied, let's not worry about this expression at all and this one also. Don't worry about these expressions for now. This frequency, omega s, is the Nyquist frequency. And 2 omega m is the Nyquist rate. To avoid confusion in terminology, 2 fm or 2 omega m is the Nyquist rate, is your sampling frequency. Like you sample at twice that signal, so that number 2 fm is the sampling rate or the Nyquist rate. Okay, so let's do some examples here real quick. When it comes to finding the Nyquist rate, to the frequency which the undersampling theorem must be exceeded by the sampling frequency called the Nyquist rate. Nyquist rate we agreed is 2 fm. Determine the Nyquist rate corresponding to each of the following signals. Now we have composite of signals. We have this one and this one and this one. First, you need to find the maximum frequency of this signal. So the first one, what is the frequency there? DC signal, what is the frequency? 0. 1 is DC. If you want to draw it, that's the value 1. It's a constant over time. So that's a DC signal. There is no repetition, no alternating. So in this case, the frequency for DC signal is 0. This one here, we'll talk about details about sinusoidals later in detail. So generally, sinusoidals is A cosine or sine 2 pi f t plus phi. A is the amplitude, F is the frequency, theta is the phase. So let me write them. Frequency, and here's amplitude. All right, so this one, I want to look at the frequency. So I ignore anything related to the phase. I ignore everything related to the amplitude. I just look at the frequency. So I have 2000 pi t, that equals to 2 pi ft. I'm just comparing this in the parentheses with this one here. T and T will be gone. 2000 pi and 2 pi divided over 2 pi. So F will be 2000 pi over 2 pi, 1000. So the frequency of the first signal is 1000. What about this one here? Similarly, I will have 4000 pi t equals 2 pi ft. T and T will be gone. F will be 4000 pi over 2 pi, 2000. What will be the unit frequency? What will be the unit frequency? Hertz. So what is the maximum frequency here? 2000 hertz. What will be my Nyquist rate? Nyquist rate, F Nyquist equals 2 F max. So my Nyquist rate will be 4000 hertz. Is it clear? What will be the Nyquist sampling period? Basically, it's 1 over Fn. My sampling, 1 over F. So I have 1 over 4,000. Always the time period is the reciprocal of frequency. So if my sampling frequency, yeah, I have a signal or multiple signals. First one frequency is 0. Second one is 1000 hertz. Third one is 2000 hertz. I consider the maximum. And actually, it agrees with this formula here. I look at the maximum frequency. So that's why it's necessary to find the frequency of all signals and pick the maximum. All right. Second example. Quickly, we can determine that the frequency of this one is how much? Again, ignore amplitude and ignore phase. What will be the frequency of this one? By looking. See, 2 pi ft. F. 2 pi ft. That's the F. 2 pi ft. That's the F. I don't have to do the math, you know. All right, so what will be the maximum frequency here? The first one is 60. Second one is 100. Third one is 180. So the maximum frequency, F max, 180 hertz. So I need to do sampling, or the Nyquist rate should equal to F max, or larger than or equal. And that will be 360 hertz. Okay. Another example here, a continuous time signal is obtained at the output of an ideal low-pass filter. Just don't worry about this term low-pass. You've done filters before? Like the word filter in electronics. So what does the filter do? لا هذا مش فلتر هذا no, that's not a filter. Like you're talking about a rectifier. That's a rectifier, a half-wave rectifier or a full-wave rectifier. There you go, perfect. An RC circuit, RL circuit, RLC circuit. Basically, wherever you take the output, like you take high frequency component, low frequency component, low pass filter, high pass filter, etc., etc. This statement here just to tell you that my signal is band limited. That's it. And I have the cutoff frequency of that filter, omega C, is 1000 pi. So if my filter only passes frequencies below this, so that's going to be the maximum frequency of my signal. So this statement here is showing you that F max, or let's call it omega max, because using omega here, is 1000 pi. That's the whole thing of this statement, because it's a filter that has a cutoff frequency. What does cutoff frequency mean? That if my signal frequency is higher than the cutoff, it will be terminated. Only low frequency components will pass. So my signal is at maximum is 1000 pi. Then F max equal 1000 pi over 2 pi. How much? 500 hertz. So my maximum signal frequency is 500 hertz. All right, so there are 3 scenarios. I'm doing sampling. Will I get a good reconstruction? Again, the condition for good reconstruction is to sample at twice the Nyquist rate. Okay. Sorry, at twice the maximum frequency. So for each one of them, let's find the frequency and compare it with this one. So here, if the impulse train sampling is performed in X of t, which is the following sampling period, would guarantee that X of t can be recovered from its sampled version using an appropriate low-pass filter. Don't worry about the wording. It means that I have 3 scenarios of sampling period. For each one of them, I need to find the sampling frequency. And I need to make sure that my sampling frequency should be larger than what? 2 times 500, 1000. And that's it. So let's look at the first one. F of S. So that's 1 over TS. 1 over 0.5 times 10 to the negative 3. And that's going to be simply 2 times 1000. 2000. So will I go to reconstruction here? Look, I should sample at least than 1000. And this one here, I'm sampling at 2000. So it should be fine. Are you with me in this one? Reciprocal of T of N calculator. 1 over 0.5 times 10 to the negative 3. 1 over divided by half, that's 2. 10 to the negative 3 will become 10 to the power 3. So 2000. Second question, B. So that's A, B, FS, 1 over TS, 1 over 2 times 10 to the negative 3. So I have 0.5 times 1000, 500. I will not get a good reconstruction. Why? Because I'm sampling at less than this condition. I need to sample at least larger than 1000. Third one, TS equals 10 to the negative 4. So FS equals 1 over 10 to the negative 4. So 10 to the power 4, that is 10,000. Which is fine because 10 times 1000. Is it clear? Okay. Now, okay. This card. What is that question with that sampling? I believe I added it here. Okay. Okay. Courses. Signals and systems. I'll open the quizzes from last semester. Okay. Here is the question. Consider this signal x of t that is given below. 3 sine 1000 pi t plus pi over 3. List down the amplitude, frequency, fundamental period, and phase shift for the given signal. That's the first requirement. Plot signal x of n obtained by sampling x of t with a sampling ts equals 0.01. And determine the minimum sampling frequency, the Nyquist rate needed to uniquely represent the signal and discrete time, and then plot x of n obtained by sampling at t Nyquist. Let me copy this question and solve it on the whiteboard. Snipping tool. Okay, let's check audio still working. Hello. Okay, still working. Perfect. Okay, open a whiteboard. All right, so let's solve the first part. List the amplitude, frequency, fundamental period, and phase shift. Amplitude is how much? Quickly. 3. A sine 2 pi f t plus phi. So the amplitude is 3. A sine 2 pi f t plus theta or phi is the same. So this is the phi. So when you do the comparison, I have 3 sine 100 pi t plus pi over 3. So the amplitude is 3. My phase shift pi over 3. My frequency. So I have 2 pi f equals 100 pi. I don't have to put the t. So the frequency 100 pi over 2 pi. Pi and pi will cancel. That's going to be 50 hertz. All right. Fundamental period. If you remember from last week, the fundamental period is the lowest period. Let's say the signal starts repeating itself, which is the reciprocal of the frequency. So the fundamental period T equals 1 over F, 1 over 50. And that's going to be 0.02. Or you can write it in terms of milliseconds, 20 milliseconds. But in the exam, 0.02 seconds, that's still fine by me. Okay. Second part. Plot the signal x of n obtained by sampling x of t with a sampling rate 0.01 second. Okay. So let's look here. I have ts equals 0.01. Now, if you remember x of n, I want to get the discrete signal equals x of n ts. So x of n equals x of n by 0.01 times. All right, so easily x of 0, how much? X of 0 in time, though, that's almost like 2.7. Or in the calculator, you have it. You can substitute nt here, 0.01, and calculate the expression. But since you have the figure, you can give me approximation. I'm fine with that. It's just a quiz, and you're probably limited by time. Just give me, like, showing me that you know the concept of sampling. X of 1. It's going to be x of 0.01 times 1. And in this case, how much? We'll go to the signal here. So it's here, somewhere here. That's 0.1. Like negative 2.8, negative 2.9. Or if you show me in this figure itself, that this is my first sample. Okay, let me draw in red. Like this is my first sample. This is my second sample. This is the third sample. So see, sampling at multiples of 0.01. Fourth. Okay. So it will start repeating itself. 0.7. And 0. That's it. So if you want to draw it, just put the straight lines. I have a sample here, I have a sample there, etc. And assuming this is the x-axis. So that was the question, and yeah, I was, to my surprise, students didn't know how to approach this question. Yeah. Okay. So first I have x of n, that's the expression of sampling. X of n, that's the discrete one, equals x, that's the continuous function n, t of s. Now n will have varying values from 0, 1, 2, 3. It's integer values. They are the sample indices. And ts is the value given. That's my sampling period. So I substitute, instead of ts, I'll put 0.01. So it's going to be x of n 0 times 0.01. Okay. Then I start evaluating at 0, how much? X of 0, substitute n equals 0. So my first sample, x of 0, equals x. See, when you see this squared brackets, that's a discrete. When you see this one, that's a continuous. So 0 times 0.01, and that's going to be x of 0. So I acquire this value from the graph. So I go to the function, that's 0, that's x of 0. Now, x of 1 equals x 1 times 0.01. So that's going to be x of 0.01 multiplied by 1. So I go here. Where is my 0.01? This one. So this is my point. So that's the point in the y-axis. That's x of 0.01. And we said that's roughly negative 2.7, negative 2.8. It depends. At least if you reflect to me that you know this process, and don't worry about the exact value, 2.8 or 2.7. X of 2 equals x of 2 times 0.01. So you notice that this one does not change. It's my sampling period. So it's going to be x of 0.02. We'll go to the function and time 0.02. This one, what will be the value? This value approximately 2.8 or 2.7, and so on. You repeat for all other values. Is it clear now? Yeah, usually sequences we start from index 0 unless stated otherwise. But yeah, usually n starts from 0, 1, 2, 3. They are always integers, like 0, 1, 2, 3. We should agree on that. Now, whether it starts from negative 1, 3, that alone is a different thing. But if it's not stated, the default is 0. And also depending on the function. Let's say if I'm giving you the function like this. And that's from negative 10 to 10. And I ask you sample every 1 second. So I will have the negative values there. All right. The last one. I realize that drawing it will be hard. But if you want to determine the minimum sampling frequency, the Nyquist rate needed to uniquely represent the signal in discrete time, then plot x of n. So I told them just ignore this plotting part, and you'll see why. So in this signal, determine the Nyquist rate. How much? Remember, Nyquist rate should be larger than or at least larger than or equal to Fm. How much is Fm? 50. So I need to sample 2 times 50. That's 100. Now what will be my sampling period? 1 over 100, 0.01. Well, in fact, it's the same as that one. It was not hard. So I don't know why I removed this question. But yeah, plotting it is the same as having at least sample 0.01. So determine the minimum sampling frequency. We found it, that's 100. And what will be the sampling period? The reciprocal of the sampling frequency, 1 over 100, 0.01. So it should not be hard. Is it clear for now? All right. So this is the first part of the lecture. And actually, that's a continuation of the lecture of last week. So we'll continue with this lecture here. Nothing much. It's more about giving you knowledge about signals. Like types of signals, shapes, like when you see a sinusoidal, what do you expect? When you are given an exponential, what do you expect, etc. Okay, slideshow. And there will be some signal manipulations. We'll talk about time shifting, compression, expansion, shifting in amplitude, and combination of all processes. All right. So mathematical description of continuous time signals. All right, so we agree by now that continuous time signal, that my x-axis has always values. Like I don't have discrete values like let's say integer indices. And if the function does not have, like won't have values, only on discrete points in time. So in this one, if the independent variable is a function of time, t, and that's going to be the focus of this lecture, and the domain of the function is the real numbers, and the function g of t has a defined value at every value of t, then the function is a continuous time signal. It says that for every value of t, I will have f of t. Now, whether you have discontinuities is not an issue, but like you always have values of the function at time. And here are several examples here. So that's a typical modulation signal. That's a logarithmic function, if I recall well. That's a random signal, etc. All of them are cases of continuous time signal. All right, sinusoidals in general. So you have a cosine 2 pi over t naught plus theta, or a cosine 2 pi f naught t plus theta, or a cosine omega naught t plus. So it's giving you all variations of frequency. The first expression with the fundamental period, which is the reciprocal frequency. The second one with the standard frequency f. The third expression is with the angular frequency omega, which is 2 pi f. So you should be familiar with this expression, at least if you know this one, and the relationship between f, t, and omega. That should not be an issue. Just say it here, f naught and t naught, denoting that fundamental period at fundamental frequency. Okay, so graphically, how do you measure the frequency? You pick two peaks, or you measure the period and find the distance between them. That's going to be your fundamental period. Two successive peaks, and then f naught would equal 1 over t naught, and omega naught equal 2 pi f naught. Phase shift is basically the distance from the point, the x-axis in 0, like that's the 0 axis, that's, sorry, the y-axis, and here's the distance. Now, whether the shift is left or right depends on the sign here. We'll see later what we call a translation. If this sign is positive, means shift to the left. If this one is negative, shift to the right. All right. So here it's plus theta, so that means shift to the left. So this is the distance here, and that's theta over 2 pi f naught. Now, where this value came from, basically the shift should be t plus theta. So you have to take 2 pi f naught as a common factor. So 2 pi f naught by t plus theta over 2 pi f naught. So this is the value of the shift, not just theta itself, but theta over 2 pi f naught, and that's what you are getting here. And here the sign, because you're shifting to the left, so it's a negative value, but the amount is theta over 2 pi f naught. You've done that in math, I believe. Shifting in time. No? Okay, we'll see it a lot this semester. Okay, so here's an example here. It's a current in ampere, in microamperes. It's a sinusoidal. By the way, whatever is applied to cosine is applied to sine. Am I a bit fast, Adi? Okay. Exponential. That's what we call a real-time exponential. Here, A is the amplitude, and e to the power t over tau, negative t over tau. Here's tau is what we call the time constant. If you've done that in RLC circuits, or in RL circuits at least. and RC circuits. But the general expression for exponentials, x of t equal e to the power alpha t. Now alpha is positive, so what we call exponential growth. Exponential growth. Alpha is negative. What's the opposite of growth? Exponential decay. Decay. So this is an example of exponential decay, like the function, since the exponent is negative, it keeps going, and when time goes to infinity, the signal starts to approach zero. Exponential growth is kind of the mirror image, something like this. That's exponential growth. So you don't have to worry about the values, the time constant, etc. All of it matters that when you are given an exponential, that's an amplitude. When you are given an exponential, at least you know that the sign of alpha will determine the behavior of the system. And the value at t equals 0, the function will be a. So here, at t equals 0, the function is 2. All right, so we've done sinusoidals, we've done exponentials. There is a complex exponential. Usually a to the power j alpha t, and let's give it an amplitude. So here it's just saying in general, lambda is a complex constant, which is j alpha. That's lambda, like I modeled it by j alpha. Now, if you heard of Euler identity, have you heard of it? Euler identity. So this exponential form could be decomposed into a combination of sinusoidals. So it's going to be a cosine 2 pi alpha t plus j sine. لا مش 2 pi alpha t, just alpha t. There's no 2 pi there. Just alpha t. And if this one is minus, then this sign will become minus. So we can say plus minus plus minus. If the exponent is positive, so the relationship between the sine and cosine is addition. If the exponent is negative, the relationship between the sine and cosine is subtraction. Okay, so exponential complex exponentials, they have different modes. Yeah, let's not worry about them. It is determined by the values of a and lambda. So if the complex exponent includes the real exponents and complex exponents. Special cases, complex exponentials include the real exponent and complex exponent. Like it could be like alpha plus j beta. But you don't usually deal with alpha plus j beta. That's the usual thing. That's the standard one. And you see it a lot in Fourier transform. Like the function x of t e to the power minus ft dot dt. That's the integration. You can represent it in polar coordinates. This one here could be modeled by a angle alpha t. Sorry. Okay. Also, if you want to go back from this, what we call polar representation into the angular representation. So we have the real part squared plus the imaginary part squared. Let's not forget, like there's an a here. Exponential imaginary part squared under the square root. So r e to the power j alpha equals what we call imaginary squared plus real squared. Okay, but yeah, that's the expression that we will be usually dealing with. Going backwards, it's very unusual. Like it's been a while since I've done that. Okay, discontinuities still discontinuous It's not continuous in value, but in time domain it's still continuous. Like here at t equals 10 seconds, there are values. So continuous time, sines, cosines, exponentials are continuous and differentiable at every point in time. You remember, condition of being able to be differentiable is the function should be continuous. So sinusoidals in general, exponentials in general, they are completely differentiable, nothing to worry about there. Some functions have issues in discontinuities, so they cannot be differentiable. Typical example, will later on we'll see a signal called rectangular pulse or the unit step function. So many types of important signals occur in practical systems that are not continuous or differentiable everywhere. A typical example, the on-off switch, or when you have an RL circuit, whether it was DC or AC, there is a switch and you have a capacitor, something like this. So that's an RC, and we have the switch. So closing and opening the switch will cause like a spike or a pulse. So here is an example of an off switch. It was 0, then at a certain instant it becomes 3 watts. Similar thing here, the system was at rest until 10 seconds, then it starts getting values. So something probably already know from calculus, discontinuities, and their, let's say, issues that may cause some response in the system that might not be desired. All right, so the unit step function, probably that's a new concept to you. That's one of the common functions we use in engineering. Could be modeled by this expression, but for simplicity, that's the standard one. U of t equals 1 for t larger than or equal 0 and 0 elsewhere. Basically, it says that for positive points in time, the value is 1. For negative points in time, the value is 0. That's it. That's the unit step function. Now, when you multiply by 2, for example, like here, 2 u of t, then the amplitude will be 2. You just scale the amplitude and keep this expression in your mind. Like when you multiply by 2, when you divide, whatever. So yeah, again, many books define it as this. Here is just say that at the transition at t equals 0, in order for the function, to kind of have a value, it's given 1 over 2, but that's not very usual. Just modeled like this. In MATLAB, the function could be called from the signal processing library, I believe, the Heaviside function. Why is he called the unit step function? Because the amplitude is 1 unit. So here is an example of a unit step function. Usually all signals, when we deal with them, they are multiplied by unit step function. Why? Signals in real time, in our case, time is positive. To ensure this positivity to match between real life scenarios with mathematical models, we multiply each signal by u of t. So for example here, the voltage at VRC is VB u of t. It's parallel to this one here. So the voltage is VB, the DC source, times u of t, to ensure that I will only have values at positive points in time. Similar thing for all other signals, u of t, u of t. Okay. Again, ensure positivity, and some property we'll talk about later is called causality. Causality, basically, I only have values at positive points in time. I cannot have values at negative points in time, because that's a physical realization. I cannot have value. There's no negative time. There's no such thing called negative time. All right. Another signal is called the rectangular function, or what we call a rect function. Rectangular function have these values. Again, that's pretty much like the unit step function. So this one, at a certain point in time, you say we do not deal with it. It just modeled rect of t over a that equals 0 for absolute value of t larger than a over 2 and equals 1 if absolute value of t less than a over 2. Graphically, it could be easily modeled in this shape. So basically, if my value of a equals 1, in this case, I have rect of t. And if I follow that expression there, I'll have the value 1 from t less than absolute value of t less than 1 over 2, and 0 absolute value of t larger than 1/2, sorry. Larger than 1/2, and I can put the equality sign anywhere. Now, this expression here, an easier way to write it is t larger than a over 2, sorry, less than a over 2, larger than negative a over 2. That's the easier way to express that function. So another way to rewrite this expression, rect of t over a equals 1, negative a over 2, less than t, less than a over 2, and 0 elsewhere. So you don't have to worry about this expression. Because this one, t, absolute value of t larger than a over 2, it means that t is larger than a over 2, union with t less than negative a over 2. So you don't have to worry about writing it this way. Write the simple expression, and elsewhere the function is 0. So if I ask you, draw rect t over 4. From where to where? لا. See, a over 2, negative a over 2. What's the value of a? 4. So from negative 2 to 2. So it will be a rectangular function. Same amplitude is 1. From 2 to negative 2. That's rect t over 2. T over 4, sorry. Here. All right. Again, the goal of this at the beginning of this lecture is to familiarize you with different functions. So we start with sinusoidal, exponential, then we talked about the step function, and there's direct function. And later on, we will find that direct function could be expressed as a combination of two step functions. We'll see that later. There is the cardinal sign or the sinc function, or what we call the Mexican hat function. Hat. And you know another name for this one? Sombrero. Have you heard of the word sombrero? No? The Mexican hat. There you go. Mexican hat, the sombrero. All right, so that's the sinc function or the cardinal sign expressed sinc of t equals sine of t over t. So sinc of 5x sine 5x over 5x. Now, where this one is widely used, we'll see later that the Fourier transform, the Fourier of the rect will be sinc. And from duality, if you remember, Fourier of sinc will be rect. Let's not worry about values, but at least know that rect and sinc, when it comes to Fourier, they are like kind of pair. All right, using L'Hopital rule. Remember L'Hopital rule? Can you state it? What is L'Hopital rule? Okay, if it says that the limit as x approaches certain point, f of x over g of x, if it equals to 0, then, sorry, to infinity, it will lead to what? F prime of x over g prime of x. The same limit. If not, keep deriving until you reach that point. So here, take the derivative. What's the derivative sign? Cosine over 1. Cosine 0 equals 1. So that's sink of 0 equals 1. L'Hopital rule in calculus. So the plot of this function for part of the real line is shown below. Okay, so that's the 0 point and has peaks at multiples of pi, if I recall. Same here. And the maximum value at 0, that equals 1. And another property of the sink function, it does not die for infinite t. So it keeps oscillating. But we usually do approximation like from certain point to another. Now let's go to one of the widely used functions in signal processing or signals in general is the unit impulse function or the delta function or Dirac delta function. That is expressed by delta t. That's the lowercase delta. So the unit impulse function, also known the Dirac delta function or the delta function for short, denoted by this lowercase delta sign, is defined by the following two properties. See, delta of t equals 0 in all points in time unless at t equals 0. So you can express it like this. Delta t equals 1 at t equals 0 and 0 elsewhere. That's the mathematical expression of the delta sign. All right. Another property, the integration from minus infinity to infinity of delta t dot dt, that's equals to 1. That's like those two are the properties of the delta function. Another thing, if you multiply delta of t times x of t, what will be the value? We know that the delta only has values at t equals 0, which is 1. So this function will have only value at t equals 0. So it's going to be equals x of 0. You see the point? And mathematically, sorry, graphically represented by a pulse at 0. So again, assume that you have a function. You multiply this function by delta. All other values will be gone. I will only have that value of that function. So it's going to be x of 0. Any function you multiply by delta, you will get the value of the function at t equals 0. All right. Okay. Usually graphically, the delta function represented as shown below. Actually, the original, let's say, concept of delta is a rectangular pulse, but with width approaches 0. That's the technical concept. So it's here, for example, it says that if you reduce this distance here, this amplitude will keep getting higher. So as you have like an infinite value of delta, but it is modeled by this expression here that has 1 at t equals 0 and 0 elsewhere. Another thing, that's later on. We'll talk about it when we talk about signal manipulations. When you multiply by constant, so the value is that constant. So k delta t equals k at t equals 0 and 0 elsewhere. Here it's a shifted version of delta. If you remember, if I have negative value, it's shifted to the right. So shifted to the right by t naught. Okay, so graphical representation of the delta function, I believe it should be easy. So at 0, the impulse is not a function in the ordinary sense because value at the time is, if it's occurring, is not defined. It is represented graphically. Yeah, just say that it's, again, go back to the concept. It's a rectangle with unit energy. So energy here will be the distance here multiplied by the distance there. So height by width. Now, if you reduce the width, the height should go higher. If this width reaches 0, then the height should reach a high value like infinity, but it's not defined. However, it is modeled by the value 1. Delta t equals 1 at t equals 0. Again, shifting these signal manipulations, we'll talk about them later. Some properties of the impulse response. As I mentioned here, if you multiply a function by delta, that function will have value at where the delta has value. So in this one here, delta of t minus t naught, I have shifting in delta. So here I will have 0. So this is my delta at t naught. If I multiply a function with this delta here, I will have only value at t naught. So you'll have g t naught a delta minus. Actually, the delta here is no longer necessary. And you have the a value there. Sampling property. Actually, when we covered sampling, let's say we have a train of pulses, like you multiply by shifted pulses by that signal. And that's what the sampling is. You have this train of pulses, shifted versions of delta. And you just do the multiplication and you get the samples. So here is an example here. By taking a single sample of this function, you have a sinusoidal-like signal multiplied by the delta at t naught. So I'm going to get that pulse here at g of t naught. All right. Yeah, this one we don't widely use it. I will not confuse you with it. That's one of the scaling properties of the delta function. When you have scaling in time, you scale the amplitude of the function itself. Okay, the periodic impulse. Actually, that's how you do the sampling. You have delta train. That's for train. You have the summation delta of t minus nt. That's your sampling. And you just have multiple shifts or multiple versions of delta separated by t. Again, let's not worry about it. Like we don't usually do it a lot in the course. All right, now let's talk about. Now here, like previously was all introduction about signals. Now we'll talk about the signal manipulations. Signal manipulations in the form of you have amplitude scaling, you have time shifting, and you have time scaling. And with time scaling, you can do reversal left-right, amplitude scaling, reversal upside down. So let's see this example here. So let's see this function, g of t has these values, and you can summarize these values from -1 to 5 with certain amplitudes, and it's 0 elsewhere. So like from here to there. So I can only have values there. Now, why did I include the 5 and -1? Because the function will have values there. These are the zeros, but it's 0 elsewhere. And you were asked, find x of t equals 2g of t. So you want to scale this function in amplitude. Now, this one is very simple. You just go here and you just multiply these values by 2. Now, there are no change in points in time because here still the function remains g of t. So what will be the values? I'll have 0, 2, 4, 6, 8, 10, 0. That's it. That's scaling in time domain, which is very easy. How to draw it? It's going to be the same exact shape. However, my values will be 2, 4, 6, 8, and 10. Now, what about x2 of t equals negative g of t? So when you multiply by minus, what will happen to the function? Will flip. So graphically, I'm expecting something like this. Okay, that's the -5. Or easily, I have t, I have g of t, and I have x of t equal negative g of t. So I have the points -1, 0, 1, 2, 3, 4, 5. At -1, I have 0, so I'll get 0. At t equals 0, what was the value? 1. It becomes -1. At t equal 1, the value was 2. I'll get -2. At 2, it was 3. I'll get -3. At 3, I have 4, -4. At 4, I have 5. I'll get -5, 0, 0. Then I can put these values in the graph. Have something like this. Points and times the same. 0, 1, 2, 3, 4, 5. And I can just simply substitute. At -1 was 0. At 0 is -1. At 1 is -2. 3, -3, -4, -5, and I have 0. And just draw by a straight line. And that will be the output. Generally, when it comes to signal manipulations, I prefer to deal with the table part. First of all, in the exam, you don't expect this high-level function that will, let's say, take most of your time. Another thing, substituting values of t, like with this table, you can never go wrong. But at least I'll know. If I multiply by a negative value, my signal will be flipped upside down. If my time signal is, for example, if this function, I ask you x of t equal g of -t. Let's not worry about the values or the details, but at least when I look at this expression, we will later find that this is taking reversal left to right. So just to make a mirror image of this function. Now, regarding the values, I suggest you do the table part. Like you cannot, let's say, go wrong with doing the table, because it's going to be only substituting values and you get the values from the function. And usually here you will not be given the expression, you will only be given the figure. Okay, so initially amplitude scaling, when you have g of t, and same thing here, g of t, when you have 1/2 g of t, so I'm scaling the amplitude by 1/2, so I'm dividing over 2. So my maximum was 5, now it's 2.5. As the same shape, but it's kind of, shrunk a little bit in the y-axis. When you multiply by a negative value, we've seen that it's the mirror. When you multiply by a positive value larger than half, like the signal will expand. And see, in most cases here, we kind of reworked the table again to avoid miscalculations, or let's say during exam especially, you'll be a little bit under stress, you'll be fast, you may do some mistakes. So that's amplitude scaling, quite straightforward, no challenges. All right, now shifting and scaling functions. So first, we'll talk about time shifting. We talked about the rule. When you have a negative value, let's shift to the right. When you have a positive value, shift to the left. Simply consider this expression, x of t equal g of t minus 5. And minus 2 to make it simpler. Now, if you want to express this one in, let's say in drawing, let's say this is my g of t, and doing shifting. How to know that I'm going left or right? Just substitute. X of 0 equals g of -2. Now notice my new function, the 0 part, is the original function when it was at -2. So basically, I'm kind of translating my original function 2 points to the right, because that's my new function, x of t. And in shape, it equals the original function, but it's a shifted version. Shift to the right. How did I confirm? At 0, my function at 0 is the original function that was at -2. Now at 1, g of -1. At 2, g of 0, and so on. So you can, again, simply do the table, and you will simply find the answer. So let's do the table here. Now notice points in time will be a little bit varying. So let's start with t, g of t, x of t equal g of t minus 2. Now -1, 0, 1, 2, 3, 4, 5. We will later find that until 5 is not enough. Basically, because my function here, I have translation in time, I may need more. So g of t was 0, 1, 2, 3, 4, 5, and 0 here. Now here, when I substitute -1, g of -3, was there a value of -3? No. Here's -3, there's no value, that's a 0. Now at 0, g of -2, is there a value? I'm substituting here at this expression at x of 0, that's going to be g of t minus 2, g of -2, that's a 0, that's g here. Now, it's going to be x of 1 equals g of 0, of -1, sorry. That's still 0, because my function, g of -1, how much? That's a 0. Now, x of 2, g of 2 minus 2, g of 0, equals. So at t equals 0, g was 1. At x of 3, g of 1, what was the value of g when time was 1? So that's the time, the value was 2. I have 2. X of 4, g of 2. What was the value of g when t was 2? 3. Okay, x of 4, 5, equal g of 3. How much? 4. Now, did I finish? No, I did not complete all points for, I still have some values. Like when you go x of 6, that's going to be g of 4, that's going to be 5. X of 7, g of 5, that equals to 0. Now, once I reach this point, then I can tell, okay, I'm done. I'm almost like I'm done. Why? Because my maximum value of t for g of t was 5. So there'll be no g6. There'll be no use to do that. There's no need to do g of 7, etc., etc. So that's the translation and time domain, shifting in time domain. Again, by doing the table, should be easier. Here, the book is the same thing. So when you have t, and I don't suggest doing this step like t minus 1. Doing this table, let's say, to me, it feels easier. But here the book is shifting the point in time, then later start finding the function from the input signal g of t minus 1. But doing it this way should be easier. Like you don't have to do this step here. Keep in mind, negative sign shift to the right, positive sign shift to the left. Okay, so time shifting, which is also known as translation, maps the input signal to the output signal, where B is a real number. We already mentioned that. Such a transformation shift the signal left or right along with the time axis. If B larger than 0, shift to the right by the absolute value of B. So that's what you call a signal delay. If you shift to the left by using plus, if B is less than 0 relative to X, then advance in time. Okay, so here it means that this is the general expression with a minus sign. Now check the sign of B. If it's larger than 0, then expression is going to be t minus B. then that's shift to the right. Now, if b is less than 0, that's a negative number, it becomes xt plus b. That's shift to the right. Shift to the left. Sorry, shift to the left. Plus sign, shift to the left. Okay. Time shifting examples. So here, t minus 1, that's shift to the right by 1 unit. Take the function as it is, the shape, and shift it to the right. Similar thing here. And I highly suggest in the quiz and the exam, bring a pencil. Sometimes you make mistakes. You need, like, if you draw with ink, it will be hard to fix errors. Pencil is perfectly fine. Okay, so we've done amplitude scaling. We did time shifting. What about amplitude shifting? Let's say g of t plus a constant. Any idea? Well, simply if it's this one is a positive sign, then shift up by a. If it's negative, shift down by a. So let's say for this example, x of t plus 1. You will get the same exact triangle. However, at negative 1, sorry, and at 1, you'll have the function like this. Now, here it's 0, sorry, it becomes 1, and here my peak will become at 4. I shifted up by 1. So the 3 become 4, the 0 will become 1, that's it. Okay, I know it might not look the same in shape, but there is no change in the x-axis. So the function still starts from negative 1 and ends at 1. However, I'm taking the function one shift up. So here at these points, at negative 1, the function was 0. After I do the shift, then at negative 1, the function is 1. At 1, the function was 0. At 1, the new function is 1, x of t plus 1. So that's amplitude shifting. Time reversal, basically I make a mirror image of the function itself. So time reversal, also called reflection, expressed by y of t equal x of negative t. It maps the input signal to the output signal as given below. Okay, so geometrically is a reflection. So if you have u of t like this, so that's u of t. That's t, and this is u of t. And you are asked to find u of negative t. So that's signal reversal. So there's t, and this is the 0, 1, and 2, negative 1, negative 2, negative 3. Okay. So that's time reflection. Now, these are all, let's say, up to now, they're quite easy. Now, once we have combination of all, like there is a flow that we have to, to follow. Like there is an order to do. Like first, you have to do the amplitude modification, then you do the time modifications parts. Now, another variation of time is by doing time scaling, by either shrinking or expanding the function. Now, if you divide by a number, you do expansion. If you multiply by a number, you do shrinking. So time compression or expansion, also called the dilation, maps the input signal to the output signal by this expression. So t is the independent variable, a is constant. And this a is strictly positive. If it's negative, what will happen? I will have time reversal along with it. So such a transformation is associated with compression expansion along the time axis. So if A larger than 1, that's compression. Let's say x of t equal g of 2t. Then the signal will be shrunk by 2. Like, for example, going back to this example here, if I'm doing x of t equal g of 2t, it means that I will have to shrink this function by 2. So I'll draw it. So at -1 becomes -half. Here's my value. At -half, I'll get 0. 0 remains 0. 1 will become half. 1, 1.5, 2, 2.5. And the function will be something like this. But my indices 0.5, 1, 1.5, 2, 2.5. Instead of having from -1 to 5, now I'm spanning from -half to 2.5. Still the same. But let's say at -1, that's a -half. At 0, the 0. The 1, the half. The 2, the 1. So here at 1, it was how much? 2. At half, that's 1. No, it was 2. Oh, wait, I think this one is 3. This is 2. This is 1. At 3, it was 4. 1.5. At 4, it was 5. And then at 2.5, which is equivalent to the 5, it was 0. Okay. So time shifting, time reversal, time scaling. So here is the same example here. K, T, G of T. Okay, in this example here, dividing by 2. So that means expansion by 2. So instead of -1 to 5, it becomes -2 to 10. That's when you divide over 2. So you have the same exact function, -2 to 10. And at -2, it is equivalent to -1. 0 is equivalent to 0. The 2 is equivalent to 1 here. And 4 is equivalent to 2, and so on. Here's a combination of reversal and time shifting. I believe that's it for today. We'll continue the lecture next week, inshallah. Stop sharing. Okay, record. Stop recording.